Good morning. So we've actually come to the last lecture of this course. Next week you will give your presentations. So I'm going to try to squeeze in 2 applications today. Let's see how that goes. I wanted to look at the CD DVD system because that's one system we started the course with, and then we encountered it every now and then in different forms. So it's kind of a summary to look at it again, and I hope when we look at it now, things will be so much more clearer to you than they were at the start of the course. So you might have seen this picture earlier. This is a very basic layout of the optics of a CD player. Of course, there's a lot more to it than the optics, but the basic idea is you have a light source and you send light onto a disk, and the disk stores information. It's spinning, and there are motors which will move this beam or somehow move the light across this disk. So it's actually the beam is just moving laterally like this, but because the disk is spinning, you're accessing every radial point of the disk, and light reflects. And I don't know if I have that here. I don't have it. It reflects. Calibrate your pen, and somehow here the return path will go up like this. Okay, so the onward path does this. You could think of it as a beam splitter again. And the return part would go here, and it gets converted to an electrical signal, and then you have a whole bunch of electronics and image processing that takes place. That now converts this light into either data or audio or video. Okay, so how does this light reflecting off the disk carry the information? Somehow we need it to carry information. Now, in a regular communication system, the very early way of coding information into light was you want to send a word, you will convert every word into code, and that code is finally, it's a binary code, so you convert it into ones and zeros. Right? So that you just need 2 bits of information, and with those 2 bits of information, you can encode anything. If I try to put that idea into light, and in fact early communication in light, the simplest way of modulating light so that it carried information was to think of, when I'm talking about, say, sending something through a fiber, for example. You could think of switching on and switching off the light. So you have your bits of 1 and 0, and there's nothing but the laser going off, the laser going on. Okay. But we have a lot of information that we want to convey. So that's a very bulky way. If you want to convert a large volume of data into just ones and zeros, you're creating a very large volume of ones and zeros. So it's not a very efficient way of storing information. Plus, finally, you want to be able to make, for example, when you say light reflects off this disk is wobbling, how do you decide what is 1 and 0? If there's a clear system, there's no noise, you might say, yes, it's obvious. What about in a system where there is noise? I'm putting some threshold and saying above this is 1, below this is 0. So you want to have slightly more sophisticated ways of imposing that information onto light. So how is it done in the CD? And you can't think of in terms of the light alone, because the light here is falling on the disks. So the way you write that information into the disk is as important as how you read it. Okay? So there's no one unit of this which is more important than the other. This I think I showed you earlier also. I will say a CD or a DVD system, I'm using the terms interchangeably, but of course the technology is slightly more refined for the DVD, because one thing is you have a higher wavelength, and now you should know very clearly the higher wavelength does what for the spot size. You are getting better spot size, right? So you want to be able to reduce the spot size, right? and thereby put more information on it. Okay. So did I say higher wavelength? Lower wavelength. Lower wavelength will give you better spot size. So you can store more information onto your disk. Okay. So I will not go into the details of this, but the CD is a very good system to study if you want to look at how optics can play a part in something that is very interdisciplinary in nature. So all of the points listed out here are required or were required to have the development of the CD or DVD. You wouldn't have been able to get that compact system. The CD is a compact disc if you hadn't had all these developments. And you can see these developments are in a variety of fields. They're not all in optics, right? There's in coding, there's in electronics. I haven't even put in all the stuff related to the motors here, which is in mechanics. But all of these were required, and you can see the very early discoveries in 1842 and all the way till 1997 before you had a compact disc player. Okay, so it really is from variety of fields that knowledge has been pulled in to create this system, and that is true of many systems. The CD I'm talking about is now just representative, but this is true of many systems, and that is why learning optics is very useful, because you may be designing or working with systems like this, and the more you understand of every part of your system will make you do a better job of the part you're working on. Okay. Of course, you're storing information. So the big difference when the CD came out was, till then, music, for example, was not stored in digital format, but was stored in an analog format. And what happened was, you had a stylus that moved across, right? Now I've shown you some bumps over here. What is happening is, as the stylus is moving across, you can see this needle is changing its height depending on the bump on the disc. So if there's no bump, it'll fall to a lower height. If there is a bump, it'll go. And that mechanical movement was getting transformed into an audio thing. Now, but everything, every bump on that, every piece of dirt on this, everything, the stylus is responding to it. That's one thing. And the second thing is, it is also a contact method. So that needle, so if you had an LP record and you were playing music, that needle was literally scratching out your favorite song, right? And if it was your favorite song, you scratched it out many times, and eventually you literally scratched it out, right? The disc was damaged, right? So the CD made many major changes. One is, this information wasn't going to be stored analog anymore, which meant you could filter out frequencies, noise frequencies, for example. Plus, it is not a contact method in the sense there's no mechanical contact. Of course, light is falling on it, but there's no mechanical mark. So in principle, that disc is not going to ever get damaged. Okay, it is quite sensitive to humidity. It's sealed, and in a place which is not extremely humid, a disc can really last forever. But in a place like this, we may still see damaged discs because of humidity. But in general, it has a longer lifetime than the LP. Okay, let me not go through this. I think you should all know this part. So basically, you're converting the data into digital data, and somehow that digital data has to be stored on the disk. Now, an LP would initially, they would release small ones, and maybe it had one song on it, and then they would have bigger ones which would, if you have a few songs, and maybe you flipped it over, you would have some more songs, and maybe you could get 8 songs or 10 songs on it. Okay, and that was it. But now, because we've changed the way we're formatting the data, and because our desire to have more information, there needed to be a way to put more information. That's one thing. Or to see, is there some way to reduce the information? So I'm shooting a movie, I'm taking a scene, and there's a lot of, a video file is a very large file. is everything in that video file actually required for me? Okay. So the CD player is really interesting because they didn't just look at the optics and the electronics and the mechanics of it. They also looked at physiology. What is physiology? It's how the human body works. Why do you need to look at physiology? I've already given you a clue with my previous sentence. You said we want to somehow get rid of information. Okay, let's see. Physiology is a science of study of living beings, and psychoacoustics is a scientific study of sound perception. They needed people with this background to help them, and let's see why. Can you read this? Okay, this is what something that my students give me often looks like, because they're too lazy to run spell check. And if your project reports come like this, I'll not be smiling. Right? So I'm not, by putting this up here, I'm not accepting this. But the point is, though it's atrociously spelled, we can read it. I mean, if I ask one of you to stand up and read it aloud, you'll do it like this. You won't struggle, right? Because our brain is able to correct for those mistakes. Okay. So it's not that in a CD we are saying the data is scrambled, but the fact is we can exploit the way our brain works and say, even if there's some problem with the data, or even if we do something to the data, that would help us, and I'll explain what I mean by that. The point is the brain will adjust for that and give us correct information, or what looks like correct information, okay? Another important thing is, again, if I ask you to read the bottom sentence, if I had not given you the top sentence, you would still read it correctly, right? So we have removed information, we've removed crucial information, and yet you could in principle say I haven't lost anything, because I could reconstruct the upper sentence perfectly, right? So it's ideas like this that came from physiology and psychoacoustics that said, when we record music or when we record a video or for a movie, there's a huge quantum of data. You convert it into digital data and it's a large quantity of data. Now, if I say I need all that data and I have to put it on the disk, it is really very hard, because maybe you would need 10 disks for one movie, right? And you guys may be too young to remember, but when CDs first came out with movies, so you had audio CDs first for some years, then you had CDs with movies, and one movie was on 2 CDs. So you had to take out one and put in the second one, because they couldn't fit it into one, right? Now you may have 2 movies on one DVD. In fact, the really bad where they pirate it, they'll give you 10 movies on a DVD with some extra interviews thrown in for free, right? But earlier it was only, so they got better and better at doing this coding. So they are taking advantage of the fact that you can remove some information and we still correct for it. Now, in the 2 examples I've given here, you can see something is wrong and you're able to correct for it. What needs to be done when with the way data is put on the CD, it must be given in such a way that we don't see there's something wrong. But you've removed information, and what is left is enough for us just to see it as if all the information is there, okay? And so this is, yes, we did analog to digital, but you could reduce the amount of information by saying, well, if the eye is sensitive to some color at some intensity. If you have certain intensities for some time on the screen, and you immediately thereafter have a lower intensity or a different color, you could remove those because your eye is not sensitive for some time after that. If you hear a certain frequency for a certain time, for some moments after that, you won't hear other frequencies. So you can filter out those frequencies and we have not lost anything. So the trick in coding there was not to remove a lot of information and we see it's wrong, but our brain says, okay, I still know that's a man or that's a woman or that's a dog. Right? You remove information, but you leave enough that we see it as whole. And there, in that process, a lot of understanding of how the human body, especially the sensors of the human body, our ears and our eyes, how they work, was needed to say what can be removed. Okay? So this example shows you that when you're talking about discarding data, the original image is a 60 kilobyte image. You see the picture very clearly. But as you go down, when you go down to 9 kilobyte, you may not notice much difference, but you're an order of magnitude less in data, right? So you're actually throwing away some data, but it's still the resolution of our eye and maybe of the display system I'm using is adequate to just show it as almost a good image. But if we go down even further, almost another order of magnitude down, then you start to see there's a problem over there, right? So it's ideas like this that were used to reduce the amount of data which needed to be put on the disk in the space, okay? And these are the data compression techniques are what we call MP3 and MPEG and so on. And of course, you have many versions now because they keep improving on these techniques. Okay, so this is the part which really relates to this course, which is how is data stored? So I've always been saying light falls on the CD, reflects off the CD, and somehow in that reflected light is information, right? So it turns out it's not a simple reflection. It's not that there's a part of the CD which is dark and a part which is bright and we are saying there's no reflection, there is reflection, I have a 0 and a 1. That's not what you're doing. You're using interference, okay? So if you were to magnify what the surface of a CD would look like, this is what you would see, right? And you have these, they're called pits, they look like bumps, they're called pits because from the other side they are pits, right? And the region between them is land. And if you look at the side view, this is how a typical CD would look, okay? So this is the protective label, and then you have this structure, and this is where the information is stored. And you can see that you have 125 nanometer heights over here. Now, if I tell you that we're using interference, I still need to have my zeros and my ones. How are we getting the zeros and the ones now with interference? Constructive, destructive interference. So this height, I've put a number here, this height clearly is for the system depending on the wavelength of the light that you are using, because light will hit the top of this surface and some of it hits the side, and it's a reflection from both. But if you've got the height right, they will cancel out. And in this place, there's no interference here and you have a bright signal. And that's how your zeros and ones are stored, okay? Everything is encoded in this because remember the disk is spinning, but you need to read one track at a time. So you need the laser to travel across this track and then only go into the next track. It's a spiral actually, so it will just continuously follow the spiral. But because the disk is spinning, maybe your player is sitting on a table and somebody bumps into the table. It should not be that the laser suddenly shifts over here, right? We are talking about hundreds of nanometers or at the most a micron of spacing, right? It's a small distance. So it can't be that you're reading this and then you shift onto this track. So you use the track itself with feedback to say, am I on the track? And what if you had a region where you had a lot of empty space? There's no information coming back. It's just high reflection, high reflection, high reflection. So the way they code the data is that they always make sure there's a pit. Maybe the data doesn't need the pit, but it's like they have a header there. They say that if I have so many bits of data, some bits are reserved just to say, yes, we are on the track, okay? So there are many different types of coding that were developed especially for the CD. They may get used in other systems as well, but everything is done based on light reflecting off that track. So you're keeping the light on the track using that reflection, you're getting the data off the track using that reflection, you're ensuring that you don't switch from one track to the other using that reflection. Okay? Okay. So so this is what I was saying, you have light reflect from the top over here, light reflect from here, and what you will see is if you have got this height right, A plus B is going to give you perfectly destructive interference. Here for the CD, they started with 780 nanometer wavelength, okay, a little bit in the IR, and therefore the height was around 125 nanometers for cancellation. So this is what it looks like. Now that's the spot on one bit of data, okay, and you can see the spot has to be larger because you need that interference to happen. So you need light to fall on the land region and light to fall on the pit region, and that has to interfere with each other. So the spot has to be slightly larger, but there are two other spots, okay. Why do you have two other spots over there? As I said, those spots should only lie on this land region which is between tracks. So you're monitoring the reflection of all three spots. If you start seeing information in this spot or this spot, you know that the central beam is moving off the track. So you're using feedback. This spot and this one should give you a uniform constant intensity all the time. And if it starts getting modulated, then you know that you're moving off track. So that's used as feedback to keep the central spot on it. How are these three spots generated? We don't have three laser diodes in there. We have one laser diode and a grating, a diffraction grating. Now we couldn't do diffraction in detail, but you will be doing experiments today in the lab. And the grating is nothing but a device which has a periodic variation in phase. Okay, so it continues and this distance is repeated. So in this diagram I've drawn it with a height variation. That means if a beam of light is incident on this, periodically parts of the beam go through a slightly longer path length than the other parts. In other words, this device is generating a large number of beams with slight phase differences between them. And because you know in interference, when I have two beams interfering, some places will have constructive interference and some destructive. The grating is now no longer two beams of light, it's many beams of light. The place where constructive interference happens is going to be very limited. Okay? A good way to think about it is, if I have two beams of light, I get constructive interference over a larger area. I get destructive in some places, but I get constructive. Both of these happen over a large area. Okay, that's like having two people in the room and maybe you can get them to agree on some things. Right? Now put 10 people in the room and say, let's see how many things we agree on. Agreement is going to come down drastically. Put 100 people in the room, and especially if they're from IIT, the number of people are going to agree is even. So the points, the places you agree on are going to be less, and that's kind of what's happening in interference. Constructive interference happens when a certain condition is met, and it gets harder to meet that condition the more beams you put in. So the places where that happens in less places. So a grating will give you very sharp lines, and you'd say this is where constructive interference happens, and it doesn't happen anywhere else. Okay? So the grating creates out of that one incident beam several spots, and in fact it has a 0th order and 2 higher orders, and that's what we're looking at over here. Okay? And you can see as the smaller wavelength will give you smaller spot size. So the development in technology was the CD started with 780 nanometers and the original discs could store 700 MB of data. But the DVD shifted to a slightly lower wavelength and they could do 4.7 gigabytes of data per layer, and some DVDs actually had 2 layers of information. Okay, and the Blu-ray discs were so called because they shifted to blue light, right, and that was 25 gigabytes. So you could either put more information or the quality became better because you didn't have to use that much compression on the data. Okay. Okay, so this is schematic of a pickup head from a Sony system, and this is the laser diode over here. Okay, this is the diffraction grating. So this is just one beam of light, but when it hits the grating it gets split. So these 3 lines here just to show the spread of the light coming out of the laser diode, but when it hits this, it forms 3 distinct beams because of the grating. This is a beam splitter. In this case, they've used a polarizing beam splitter so that the light coming out is polarized in one way and it initially will get reflected. So this beam splitter reflects one polarization. Goes to this mirror that turns it around, sends it through this lens that focuses it onto the disc. Okay. The interference reflected light comes back, and through the process of interference actually or reflection here, there is a polarization change. So in this system they have not put anything to specifically change polarization. In some systems they may actually add an element that will rotate the polarization. Here there must be something on the way. You can have a polarization change in reflection, so they may be exploiting that, so that the returning light is of a different polarization and therefore will pass through the beam splitter and not get reflected. Okay, and then it goes to this photodiode, but it's not one photodiode anymore. It is a set of an array containing 6 actual individual units. Okay, it's all together, but you could read them separately. Do you remember at least why we needed this 4, this A, B, C, D? We talked about it when we talked about aberrations. When we talked about how you could use an aberration in a good way. It is so heartening to see how you have all absorbed optical engineering and throwing back what I taught you at me. What aberration did we use in a positive way? What are the aberrations? You remember that? 5 monochromatic aberrations. What are they? You don't remember the 5 monochromatic aberrations? Mathu, spherical, astigmatism, coma, distortion, curvature. Okay, right? You remember that we used one of these in some way? We said that if you have astigmatism in your system, the spot will no longer focus to a circular spot but an elliptical spot. So we use it as feedback. I've drawn this as a nice static system over here, but this disc is spinning. And you saw that the variation in height of the pit was 125 nanometers. That means I must get that right. The focal length can't shift too much. So if it's spinning the beam, what if there's a little jitter or movement in that? How do I make sure that I'm getting that focal position correct so that I'm getting back the light reflected correctly and they're interfering correctly? Well, if you look at this, the lens is here, right? This is the lens, but it's got these control coils over here. So they are used so that the lens can be moved up and down or sideways. Up and down is to ensure you're always on focus. Sideways is to ensure you're always on the right track. Right? Now, if I have a circular spot here, I may be doing A plus D minus B plus C. If I have a circular spot aligned correctly, this signal will be 0. If on the other hand, we have an elliptical spot, then this is going to be negative. And if we have an elliptical spot like this, it's going to be positive. So I can tell exactly how the lens should be moved such that I keep the spot focused on the layer of the data layer of the disk. In addition, the two, so I have A, B, C, well, let's call them something else, X, Y, Z. Y is this signal, Y is coming back to the center of your detector, X is falling here and Z is falling here. They must be of constant uniform intensity because they should fall only on the region of land between the spiral of data. If they start getting modulated, it means the whole beam has drifted. So you're monitoring all these signals and using it as feedback, which is going back to this lens, which has, it's a lens with magnetic coils, right? And that allows you to move the lens accordingly. So of course, there's a lot of electronics that's happening here, right? And the electronics is, the aim is to make this optical signal useful, to ensure that you're getting correct data. Now you notice this laser diode, the laser diode over here. Why is the outer facet tilted like this? You know, when I usually draw a source, I'll say here's a laser diode and here's the light coming out. But this one, it's drawn like this. Why is that? Pardon? Okay, so it could be that well, it's not Brewster angle, because Brewster angle means you want reflected light to have a certain polarization, right? I don't want any reflected light here. But you're getting the idea. Why would I want it to be like this? You don't want light going back into your source. So although you have used a polarizing beam splitter, ideally no light should come back. There's always a chance, and maybe at this point it hits the grating and there's some reflection. And when light comes back onto this surface, it will go right through. Whereas when it comes back to this surface, Snell's law tells us a lot of it is going to go off at this angle and not enter. Some light may transmit, but there's less light going in compared to what is coming out. Okay? So these are simple things. But now that you are familiar with optics, you should be able to look at a system like this and understand why you have even why the window of a device may be tilted and not flat. Okay? You may have a thin film coating on it also to prevent, there are so many things that could be. If he does find the pickup, you will see that the lens of the pickup has a colored tinge. Because it has an anti-reflection coating at the wavelength of use, it will have a color of a different wavelength, right? Okay. I will not go, this is what the lens, so the lens is here and this is the coil. So you send a current and it will magnetize, and so you send a current based on the feedback. Does the lens have to move laterally, left or right? Does it have to move up? Does it have to move down? Right? So that's your tracking technique. These are the 3 spots generated by the grating. I can design a grating so that I don't have 3 spots. So a grating, as I had said, it's a structure like this with a periodic variation in phase. Right? It may be larger. Light is incident and travels through. But each of these sections now, some parts have gone through this height h and the rest has gone through air, and this height h has a refractive index n. So I can choose such that I have 0 light in the first, in the same direction as the incident. So NH is the path length. That means a phase seen by those parts of the beam is this. And I want this to be destructive. I don't want light to carry through. Okay? That means if I pick the height to be lambda by 2n, is that right? Yeah, lambda by 2n, then I will, yeah, you can keep it there. Then you can destroy the 0th order. But the light has to go somewhere. So what will happen in the grating is, if you illuminate such a grating, you will get light in a first order and light, so you will have a -1 order and a +1 order. You will not have a 0th order. How do you achieve that? By choosing the height correctly. In the case of the CD player, you want a large 0th order, because that's the beam that falls and reflects off and carries the information. So you won't have a grating with this satisfying this condition. It will not satisfy this condition, so that you have light in the 0th order. But there is some light going into the higher orders as well, and that is what you use for the tracking. Okay? Okay. So as the beam, if you are going out of focus, as you go out of focus, the signal from this curve will look like this, and so you can tell not only how much you are out of focus, but in which direction you are out of focus, and thereby send the correct signal to the lens and correct for it. Okay. Yeah. So I'll stop with that. Okay, for this application. Do we have time? Yeah, we have time to look briefly at the other application. You can just pass that, pick up a head around. So you should be able to see the lens, and it will easily shake because it's held by those coil, right? Yes. If you have UV light source, yeah. You can, but once you go into UV, you can't use all the same glasses and so on. You need different glasses for that. So up to blue is, you can use these glasses. Then costs will start going up if you change to UV. You can't use the same glasses. All glass absorbs UV. That, I don't know, do you have photochromatic glasses? Have you heard of photochromatic glasses? No? Yeah, so photochromatic glasses are you can get when you get your glasses made, it's much more expensive, but you can ask for photochromatic glasses. That means when you go into strong sunlight, the glass will darken. Well, it's strong sunlight, but it's actually strong UV. So you could go, if you go up into the mountains and it's really cloudy, the glasses will change. They'll darken because there's some extra chemical put into the glass which changes the nature. So when it absorbs UV, it becomes non-transmissive. Okay, but all glass absorbs UV. So you can't use, then you have to use special glasses, special materials, and it becomes quite expensive. But in fact, in the semiconductor industry, they use light to write patterns, and we put more and more chips onto a device, right, onto a wafer. They use UV there because that's a very expensive system. It's one system and they do it. But for these commercial systems you want to mass produce, then you want to bring down the cost as much as possible. Extreme UV is used in lithographic systems because smaller wavelength means you can write very small features. So his question is, does the laser damage? We talked about, we've switched from the scratching LP model to this. You are not sending that much power to damage the power is very low. It's not, as far as I know, it's probably even eye safe, but it's definitely, it's not high power. You get CDs you can write on, right? So here I'm telling you how you read, but you can also write on CDs, right? So there the disc has a material which is sensitive to light, and there the writer will have higher power because it has to cause a chemical change, a permanent chemical. Well, you even have rewritable CDs, but it has to cause a change. There the power would be higher. But the typical CD writer, the power is low, it does not damage. This is CD reader. We are only reading the data. I can't use the same thing to write because I will need a different wavelength, and you get special discs to write on. You're reading, no? The information is already on the disk and it's reflecting off. And so in the writer, you're not, in the disk I showed you, you had these patterns, right? And if you looked at them, it meant it was something like this, right? So there are height variations in a disk you're reading, but the writing disk is slightly different. There you're crossing phase changes, you're not removing material. There in the writable disk, you would have a disk like this, and then say you expose it here, there's some change that happens and the refractive index changes here, and then you don't expose it in the next region, and then you expose it here and a refractive index changes over here. So now I have a varying phase change. That's the same thing I have here. This is nothing but a varying phase change. And if you have a rewritable disk, you would flush this with some light which undid the change everywhere, and then again I could write on it. So you may actually have different heads for reading, for writing, because you need different wavelengths. Yes, yes. You may get it as a combined unit, but it's two different sources of light. They may have combined it in some way that there's a mirror that moves one into place and the other out. But it is two different sources of light, yeah. And with two different powers also, because you need more power for writing than for reading. Okay, we really don't have much time, but I want to just introduce the other topic to you, because a lot of these applications were finally relating to interference. Although the CD player used your knowledge of aberrations and polarization, and so it really, I like that system for this class because it kind of covers everything that you have done. But I just wanted to talk about this. We have a few minutes and I will. So I'm sure you've all seen this, right? I hope none of you have had to use it, but you might have seen it either somebody in a movie, in a hospital, or if you visited someone in a hospital. It's measuring, it's called pulse oximeter. It's measuring the oxygen level in your blood. It's known also as oxygen saturation, and basically hemoglobin is what carries oxygen in your blood, and it's measuring therefore how much hemoglobin has oxygen in it. You can have hemoglobin with oxygen and without oxygen, okay? This is a very important measurement. It generally tells you, the status of a patient. So it doesn't matter what your illness is. You need to know that the patient, the respiration is happening properly and there is enough oxygen. And so this is something you want to monitor continuously. And if you're monitoring continuously, it means that when the device is on the patient, it must be as non-invasive and troublesome to the patient as possible. Okay? second. It clearly must be as small as possible. Okay. So what it needs to measure is how much hemoglobin has oxygen compared to how much does not, and it's that percentage which we call the oxygen saturation, which is of interest. Okay. So it's not interference, it's just using light absorption. So the outer case of this device that you clip on to the finger is shown here, and there are two sources of light, and you can see that light will travel through the finger and reach the detector on the other side. Now somehow you are going to use absorption to tell you how much oxygen is there in the, or how much oxygenated hemoglobin there is. The absorption depends on various things. You can, I mean, you should imagine straight off that if I'm just measuring the light that's coming to the detector, if you take the people sitting in this room, we all have different skin color, right? So some people will, there'll be a lot more absorption just because of the color of the skin. Some people have very slim fingers, some people have very fat fingers. So it could be how much length it has to go through. That may have nothing to do with, we may both have the same percentage of oxygen, but somebody may have fatter fingers, sounds bad, but somebody may have fatter fingers than someone else. So you cannot be saying they have less oxygen because it so happened their finger was fatter. So you somehow have to take this into account. But basically you're using absorption. Okay? So we know that concentration of the light absorbing substance, the length of the path, and how we use it is that it also depends on the wavelength. So that's the trick we're going to use, that oxygenated blood and deoxygenated blood absorb differently at different wavelengths, and we can use that to adjust or correct for the fact that all of us have different thicknesses of finger and different colors of skin and so on. Okay. So the basic idea here is what is called Beer-Lambert's law. You might have encountered this elsewhere, and you're just saying that this is the absorption coefficient, and that depends on how much oxygen, or what is your oxygen saturation, and x is the length of the path traveled. So this is the basic that we're using. Okay. Okay. So what we're saying is that if you look at the deoxygenated blood, its absorption is much higher in the red than it is in the infrared, and if you look at the oxygenated, it's got a higher absorption in the infrared than in the red. And you use this ratio of the absorption at these two wavelengths, and you can calibrate your system therefore to say, is there more deoxygenated or less? In other words, you can actually get the saturation. Okay? I will not go into the details, but I wanted to introduce this system to you just to say that optical systems come in all kinds. Okay? They can be as complicated as the CD DVD player, where optics plays a small role and you're using some geometric optics, you're using some interference. It can be as simple as sending a wavelength through something and measuring the output. You have to take into account all the factors that would change, and in fact they are databases, because these numbers would vary for Indians compared to Europeans, compared to Eskimos, right? So you need to have a database for the general group of people that you would be using this system with, right? Let me not go through all of this. Okay. So what I wanted to end with is that if you think about it, there are a lot of issues here. It's a very simple system. The idea is very simple, but there can be also a lot of problems. And again, optics is one part of it, but you also need to worry about the signal processing of it. It's a very small signal that you're measuring. So in addition, what they do is they look at and the signal will vary depending on where you are in the pulse, right? Is it pulsing blood towards that part of the body or away from that part of the body. So you'll actually see these variations here, which is why it's called a pulse oximeter, because you can also extract pulse information. But that signal is a very small signal over a very large background. So you need a lot of fancy signal processing to pick out this pulse information correctly, right? So there are a lot of, and when you patient moves around, it's moving around, and the signal should not change because a person moved. It has to stay constant. So there are a lot of issues that you can think have to be approached. Why I wanted to bring it to this class is, right now every pulse oximeter in India is imported as our most medical technology, right? So that's a place where you people should or could step in, because every hospital has, almost every patient now has a pulse oximeter. So maybe you can really earn some money over there. Okay? Okay. So I'll end with that, right? You have a lab in the afternoon and next week presentations, but you need to submit reports. Today I think was the last day, so please do that. Okay, any questions? No? Yes, there are 2 detectors for, I'm sorry, I rushed through that. I mean, it could, here it's just shown as 1 detector. It could be that you're looking, these are, it will probably be 2 detectors, because one is in the red and one is in the infrared, right? So you're looking at the absorption of both, and you have to do a lot of calibration. I didn't want to spend time on that, but you have to do a lot of calibration because you have to take what is the absorption of the red light, what is the absorption of the infrared, and because you're making these 2 measurements, they're both seeing the same thickness of finger, and they're both affected by the the lightness of your skin or the darkness of your skin. So those factors are sort of getting cancelled out by looking at both of those, right? And you take the ratio of that, and but the calibration involves patients who are given less and less oxygen, right, under controlled conditions, right? So you actually will physically, they'll take blood samples and measure to calibrate the system initially, the first time. They will actually reduce oxygen levels and then take blood samples and measure and say the actual measurement says so much. So they'll do their calibration and ensure the machine is showing that much. I'm sure that no people were killed in the process of calibration. I hope. Okay.